So I'm going to record how to do the energy problem. So we first start by defining our system with a dotted line. Then we list what types of energy are present. Then we decide whether energy enters or leaves, and if so, we draw some arrows and we make the pies bigger or smaller. And finally, we make slices of pie to represent the energy or the potential energy that is stored. So looking at this example problem, I first draw the dotted line around the system. In this case, it's going to be the ball and the ground. And now I decide what sort of energy here is present. I'm going to say that kinetic and thermal energy are present because all objects have thermal energy, just a little bit, and because this object is moving, at some point it's going to have some kinetic energy. I'm also going to say that it has some gravity energy because it moves from a high place to a low place. And now I got to decide whether or not energy enters or leaves the system. I'm looking at this and it looks like energy is just transferred. From here it's all gravity and here it becomes kinetic. So no energy enters or leaves, it just gets transferred. So I'm going to draw my pies like this. I'm going to start out by drawing all the same size circles because the amount of energy in the system here stays the same. In the beginning, in step 1 here, all that energy is stored as potential energy due to gravity. So I'm going to put all of that energy as PE gravity. Okay? Since I can't measure that energy, I'm just going to call it potential energy due to gravity. Now here in our second diagram, it gets transferred into kinetic energy. So I'm going to say that half of its potential energy is transferred into kinetic energy. So this pie will represent energy kinetic. Now I'm using just an E here because since the object is moving and we can measure its speed, we can measure the kinetic energy. Okay, the potential energy is just stored. It's in the object, but we can't measure it yet. We just know it's there because it's above the ground. Now some of you might say that, well, everything has thermal energy, so you can say that it has a little thermal energy here because that object is not absolute zero. And then this one will also give it a little bit of thermal energy. Okay? Now, in step 3, we are looking at the ball right before it hits the ground. I'm going to say that all of its gravity energy, all of its potential energy due to gravity is gone, and it is all turned into kinetic energy. So I'm going to say it's all energy kinetic. And since I did put a little sliver of kinetic or of thermal energy before, I'm going to put that little sliver of thermal energy. Okay? So now I'm going to show you how to do the next problem. So, down lower, I'm going to talk about the wind-up toy. So with the wind-up toy, I look at this and I first draw my dotted line to represent my system. So it's going to be the toy and the ground. Now I got to see if any energy is gained or lost. Now what's happening here? It looks like the arrows represent speed, so it looks like the thing slows down. So if it slows down, it had to slow down for some reason. My thought is that potentially inside that rabbit, it ran out of, we wound it up and we gave it some energy and then it kind of bounced along. And so I'm going to really say that maybe it just, well, it didn't really lose any energy. Okay, if we just said our system was just the rabbit, then we would say it loses energy to the table. But since we're adding the table to our system, I'm going to say that it doesn't lose any energy. So it's all the same size. Now in the beginning, I'm looking at that, and since it's all wound up and it has a lot of speed, I'm going to say that it's got a bunch of kinetic energy because arrows represent speed and it's going fast. So it's got a bunch of kinetic energy. And then saying, well, why is it going across a table? Well, it has some sort of spring that's all wound up, some sort of gears in there. So I'm going to say that it has some mechanical energy, but it's potential. Okay? Now, as it goes down the table, it uses up some of this potential energy and it turns it into kinetic for motion, but it also drags against the table and it also gets kind of hot, so it the thermal energy increases. So I'm going to say that, let's get rid of some of those stray marks. Ooh, I put K, but I meant mechanical energy here. So in this second box, number 2, I'm going to say that this object has maybe a little less kinetic energy because it's going slower. I'm going to say that some of its mechanical energy has been used up, and all that's left is a bunch of thermal energy. The thermal energy is stored inside that rabbit. Probably the gears heat up as it moves along, and in the table because it scuffs across the table and heats up. Okay, now finally when it stopped, it has no kinetic energy left. Probably has very little potential energy left, so all that must be left is some thermal energy. Finally, I want to show you this bike one. Okay, this one the little boy got cut off, so this is the boy on the bike. So that's my pitiful drawing of a boy on a bike. And what's happening? He's going slow, faster, and fast. Okay? Step 1 is defining my system. I'm going to define my system as the boy, the bike, and the ground. Since I added all those things in my system, really, no energy was lost because the boy's energy inside of him made him have some speed, and then that caused him to get faster, and then faster here, but all his energy just transferred from inside of him to here. So now I gotta list what kind of energy was present. Well, the boy has chemical energy, potential energy, chemical, because he's got food inside his belly. Okay? As he starts moving faster, he gains some kinetic energy, probably loses some of that chemical energy. Okay? And then I would also say that some thermal energies are going on here because those wheels on that bike are scuffing against the ground and probably getting hotter. So if I'm drawing some pie charts here, they're all the same size because everything here is in my system. And in the beginning, I'm going to say that he has mostly chemical energy inside of his belly. He burns his chemical energy to get some motion for his legs, and his legs push the bike, and so I'm going to say that about half of his chemical energy has turned into kinetic energy because he's gotten faster. Now, the boy is also getting hotter because he's sweating, right? He's sweating and his bike tires are getting hotter. So in that system, a little bit of thermal energy has now appeared. So I'm going to label that thermal energy. Okay? Now after a few minutes of riding, he's going really fast. So he's got a lot of kinetic energy. Okay? Lots of kinetic energy. And he's probably also got a lot of thermal energy because he's all hot and sweaty and his bike tires are rubbing against the ground. But he doesn't have that much chemical energy left because he's probably used up a bunch of the food in his belly to get him pedaling. So there is the correct way to draw pie charts for this scenario. I'm going to just show finally. The final one here is about the car. We did this one in class. We said that the car, if we define our system as the car and the ground, then, so if we define our system as both the car and the ground driving, then the energy all stays the same. Okay? So the energy, stays the same because any energy that the car loses, it goes to the ground. So if both of them are in our system, it stays the same the whole time. The car has the same amount of kinetic energy the whole time because it's going the same speed. Now the car has lots of potential chemical energy here because it's got a full gas tank. Here it's used up some gas, and here it's used up even more gas. And this thermal energy is the heat of the car because the car's engine gets hotter. So Here is when the car just starts, here is after driving for a while, and here's after driving for a long time. Okay? Now, I'm going to redraw this saying that only the car is my system. So now, in red, I'm going to define my car only as the system. So if just the car is my system, anytime the car loses energy, it's going out of the system because it's heating up the ground. So in this case, if just the car is my system, I'm going to start out with a big pi. I'm going to go to slightly smaller and a slightly smaller. And in the beginning, this car is going to have a lot of potential energy chemical because it's got a full gas tank. Okay? It's moving, so it's going to have a bunch of kinetic energy. Okay? And we can give it a little sliver of thermal energy because everything's got a little thermal energy. Now, after it's moved for a little while, it has lost energy. So lost energy to ground. And what sort of thing? How did it lose energy to the ground? Well, I'm going to call that friction because the tires rubbed against the ground. So it lost some energy due to ground. So it's going to have a little less chemical, but the same amount of kinetic energy. So this one represented kinetic. I'm going to give it roughly the same amount of kinetic. Now again, it looks like this pi has more, but you can see that the whole pi is smaller. So I made it slice slightly bigger like that because I wanted it to approximate the same area of this. Okay? Then finally, I'm going to say that it's lost energy to friction because it lost it to the ground, and right now it's going to still, so I look at this amount of area, I want to draw this much area right here. So I'm going to kind of draw like this much. Okay, and that's probably, that's about the same. And then I say it's got barely any gas left. And then maybe still has a sliver of thermal on each side. Okay, so again, the key point here is that since we drew our system as just the car, we're saying it lost energy each time. Okay, if we draw our system as the car and the ground, we say the energy stays the same. It just gets transferred from the car to the ground, but the ground is still part of our system. Big difference here, thermal energy got increased each time because in this example, the ground is getting heated up by the car. And in this example, the car is losing that energy to the ground. So it's a little bit different. We could then say that each of these thermals maybe gets a little bit bigger, and that's why I recommend doing this in pencil, so you can always go back and add a little bit more or subtract a little bit more.